The last thing we need to look at with position graphs is how to actually do math or numeric calculations by looking at a position graph. So let's draw an example. In order to do math, we're going to need actual numbers. So let me write some numbers along the side here. This is my time axis, which is usually in seconds. And then I'll do some bigger numbers on the side. Let's go by tens. So this would be position, which is usually measured in meters. All right. Let's make a graph. We're going to go up to 50. All right. Notice that this graph has two unique sections, and we are going to deal with them separately. So I'm going to call this one segment 1, and this will be segment 2. The first thing you need to remember is that slope of position equals velocity. So if I want to solve for the speed of this object, then I need to figure out the slope of my graph. To find the slope, you need to identify 2 points. So I'm going to pick, for segment 1, the beginning and the end point. So the first point at time 0, my graph started at position 20. And later, notice if I line this up, this is 3 and 50. So after 3 seconds, my graph was at position 50. Once I have those points, it's easy to do slope. I just do rise over run. So rise over run. And remember that the rise is the y-axis. So this graph went from 20 to 50. That is a rise or an increase of 30. And the x went from 0 to 3. So that is an increase of 3. And remember that both axes has units. So the rise, or the y-axis, had the units of meters, and the run, that's your x-axis, had the units of seconds. So notice I'm going to get an answer that is meters per second, and those are appropriate units for velocity. On the computer, you should never leave your slope as a fraction. You need to put it in a calculator and get a number or a decimal. In this case, 30 divided by 3 is 10. So this object had an initial velocity of 10 meters per second. I'm going to write that on the graph so that I don't forget. Okay. Next, let's look at segment 2. We need to identify our points. So segment 2 goes from 3, 50, and then it ends at 6, 10. Okay. So once again, I'm going to do rise over run. The rise is the y-axis. So we went from 50 to 10. That was a decrease of 40. We show that it was a decrease by putting a negative. So I went down 40. The run is the x-axis. So that's from 3 to 6. That was an increase of 3. And once again, we will get the units of meters per second. This is a number that I'm going to need to put in my calculator. So 40 divided by 3, I get negative 13.3 meters per second. So notice this second segment is actually a little bit faster. It used to be 10, now we're at 13. So not only did the object turn around, but it's also going faster than it was before. So 13.3 meters per second. The negative just reminds us that it's going downhill, which means towards the reference. That's the first calculation you can do on a position graph, but there is one more calculation that I want you to be aware of. Let me erase this. Sometimes we aren't interested in the individual pieces, but we're interested in the overall graph. This is called the average. And what we do to make the average is we just look at where the graph started and where the graph ended, and we ignore what really happened in between. And I'm going to connect these dots with a line. That line that I just drew is called the average line. And we can calculate a number for the average the same way we do the other slopes. So notice the average started at 0, 20 and it ended at 6, 10. So this is the overall graph, ignoring the actual red path, which is what really happened. And I can apply rise over run. In this case, the y values decreased by 10 and the x values increased by 6. If I put that in a calculator, I'm going to get negative 1.7 meters per second. In this case, the average was very small because the object turned around. Anytime that you turn around, it weakens your average velocity because you're going the wrong way. So that is how we calculate and draw the average for a position graph.